Okay, so in this video we're going to be looking at some of the reactions of the halogenoalkanes, and we're going to be looking at the next core practical 4, which is investigating the rate of hydrolysis of a halogenoalkane with both water and with an alkali. Okay, so we're on page 12 of your notes and we're looking at the hydrolysis of the halogenoalkane. So to prepare for this, I'm going to put 1 centimetre cubed of potassium hydroxide. It's the hydroxide in this case which is going to act as the nucleophile. In ethanol, and we talked about this before, but ethanol is a very good co-solvent. It has both polar and non-polar characteristics, so it will take both the potassium hydroxide and the halogenoalkane into solution. We also need an equal amount of water because technically what we're doing is a hydrolysis reaction. To that we're going to add our halogenoalkane. In this case we're going to use 2-bromo-2-methylpropane and shake the test tube for a few minutes. So that reaction will then work. It will work quite quickly because we're using a strong nucleophile like hydroxide ions. But the products produced are all colourless, clear solutions, so we need to identify the fact that it's worked. So what we're going to do is we're going to test for the bromide ions. And we're going to do this by acidifying it. That will get rid of any hydroxide ions. If we didn't do that, the silver could react to form silver hydroxide, which would also appear as a precipitate. So we need to acidify it to remove any excess hydroxide ions. Then we can add the silver nitrate. If it's worked, if bromide ions are present, we will get a cream-coloured precipitate of silver bromide. Okay, so the new organic compound that's been formed is an alcohol, because I've replaced the bromine with an OH group. In this case, it is actually a tertiary alcohol, because I started with a tertiary halogenoalkane. Ethanol was added, if you remember, as a co-solvent. It has both polar and non-polar characteristics. So it can take both the potassium hydroxide and the halogenoalkane into solution. The precipitate is very simple. We've got some silver ions, that's from the silver nitrate, and I've added bromide ions because remember they've come loose, they've been substituted for by the OH group, and that makes the silver bromide precipitate, and that's the cream precipitate that you see. The reaction with the halogenoalkane, so again we're going to use our halogenoalkane that we started with. We're going to use the tertiary halogenoalkane, and I'm going to add my OH negative ions, and they're going to make my alcohol. Here the OH negative ions are acting as my nucleophile, and I kicked out the bromide ions. Okay, so we're going to have a look now at the comparison of the different halogenoalkanes. We're going to look at 2 experiments. First of all, the effect of the nature of the halogen itself. So in this case, I'm going to have 3 test tubes which have different halogenoalkanes in them. 1 chloro, 1 bromo, and 1 iodo. To each of those, I am going to add 4 centimetres cubed of silver nitrate to each halogenoalkane. I'm going to put them all into a warm water bath, and I'm going to time how long it takes for the precipitate to form. In this case, my nucleophile is a little bit more difficult to identify. We do this in aqueous. So actually my nucleophile is the water. Water, the oxygen has a lone pair on it, so it's actually the water in this case which is acting as a nucleophile. Okay, so here we have our chloro and our bromo and our iodo halogenoalkane, and this is one of the experiments. If you go onto the PowerPoint, this is one of the videos that we point you to. But you can see there, as we add the silver nitrate, the iodo changes almost immediately. The chloro and the bromo, you can just start to see that the bromo is starting to produce a precipitate. It's going a little bit cloudy. It is quite, that one's quite a slow reaction. The iodo one happens almost instantaneously, but the bromo is quite slow. But you can see there clearly it is starting to form a precipitate, so it's coming second. So iodo was the first one to form precipitate, then bromo, then chloro. Okay, so back in our packs we can write in these observations. So 1-chlorobutane would eventually have formed a white precipitate. 1-bromobutane forms a cream precipitate, and the 1-iodo forms a yellow precipitate. The iodo one reacted first, the bromo second, and the chloro third. Okay, so which of these is the most polar halogen carbon bond? Well, that would be the CCl. So this will have the biggest dipole on it. So it's delta negative, delta positive. Which is the biggest halogen carbon bond energy? In other words, which is the hardest bond to break? Well, again, that would be the carbon-chlorine bond. And the next factor we need to consider is which is the most important when considering the rate of the reaction. Is it the polarity of the bond that's important, or the strength of the bond that's important? If it was the polarity of the bond, if this was the most important factor, we would expect the carbon-chlorine bond, or the chloroalkane, to react quickest, because this is the most polar bond. The iodine carbon is still polar, but it's only just slightly polar. So if polarity was the most important factor, this is the molecule which would have reacted first, the chloroalkane. We know it didn't. So it must be down to the bond enthalpy, and this is a much more important factor when considering the rate of the reaction. It's the strength of the bond, and because the iodine carbon bond is so long and so weak, it's that factor which determines the rate of the reaction. So it is the bond enthalpy which is the most important factor. Okay, looking at this second experiment, we're going to look at the effect of the nature of the carbon skeleton and what effect that has on the rate of hydrolysis. So we're going to use the same halogen this time, but we're just going to change whether it's a primary, secondary, or tertiary. So we have a primary, a secondary, and a tertiary. Okay, so they all form this cream precipitate because they're all going to form silver bromide. But in this case, it's the tertiary reacts first, then the secondary, then the primary. Now the reason for that is due to the mechanism that they have to undergo with water. So the order of the rate of the halogenoalkanes is the tertiary is the fastest, then the secondary, then the primary, and that's the slowest. So the nucleophile in this reaction is the water. Now water is a weak nucleophile. It's certainly a lot weaker than the OH group. Because this is a weak nucleophile, it can only do an SN1 mechanism. It can't do SN2. The oxygen's lone pair is not strong enough to push out the chloro or the bromo or the halogen group. So it has to go via an SN1 mechanism. Now, the reason then that therefore this reacts the fastest is down to the stability of the carbocation. So a tertiary carbocation is very stable, or it's more stable. I should better say more stable than secondary or primary. So stability of the carbocation goes from tertiary is greater than secondary, which is greater than primary. And that explains why they have to go in this order when water is the nucleophile. When the OH is the nucleophile, it's a little bit of a different case, because then we can be going via SN1 or SN2. So we didn't need to acidify these solutions as we did in the reaction with sodium hydroxide. That was because the sodium hydroxide could react with the silver nitrates to produce a precipitate. And as there's no sodium hydroxide in that second example, we don't have to get rid of the sodium hydroxide. We acidify it simply to get rid of the sodium hydroxide. Adding a little bit of ethanol to this before adding the halogenoalkane is usually a good idea. Why is this? Because ethanol, we've said this before, is a co-solvent. It has both polar, in other words it can form hydrogen bonds, and non-polar, because it has a CH3CH2 group, characteristics, so can take both reagents into solution. Probably don't need all of that, but I'll write it anyway. So ethanol is a co-solvent, and we quite often use it not as the reagent, but just simply to get the two components to mix. Okay, so that just finishes this quick video looking at core practical 4, investigating the rate of hydrolysis of the halogenoalkanes. In the next video, we're going to be going on and looking at the other reactions of the halogenoalkanes. We'll look at that hydrolysis reaction in a little more detail, and we'll also look at cyanide ions reacting and ammonia reacting, as well as the elimination reaction. But until then, take care, stay safe. Speak to you soon. Bye-bye.